I'll share the screen. And okay, yes. So today, we will be starting with the concepts which are involved in econometrics. And the first concept which we'll be beginning with, which forms the basis of the entire econometric theory, is regression. We did regression in our statistics. So what is regression? What do you understand by regression? We've done this.
We understand the relationship between this independent and dependent variable.
Dependency.
Exactly. So this helps in identifying the relationship between your independent and your dependent variable. It will state the cause and effect. This cause and effect is the difference between your correlation and regression. Correlation also tells you the relationship between two variables, but it will not tell you which is the independent variable and which is the dependent variable. Or in other words, which is the cause and which is the effect. And this is answered by regression. So the term regression was introduced by Francis Galton, right? And you have a dependent variable. The synonyms are, it is called an explained variable. Dependent variable is called an explained variable, regressant, endogenous variable, controlled variable, predictant variable, and response. While independent variable is also known as the explanatory variable, regressor, predictor, stimulus, exogenous variable, and control variable. So whenever we did our we did our aggregate model, aggregate demand model, right? We always, like in the initial stages, we assumed that these are exogenous in nature, right? So they were our independent variables here, right? Isn't it? These were our independent variables and they were exogenous in nature, like they were not determined from within the model, but they were determined from outside the model, right? Similarly, we've done like say C is equal to A plus BY. We had this exogenous variable autonomous consumption, which was independent in nature and which was not determined from within the model. Similarly, we had income level, which was an independent variable and which was not determined from within the model. But here C is your dependent variable, right? And the value of C is determined by using these exogenous variables. Okay. So we are
here Y is also exogenous variable.
Yes, Y is also exogenous variable.
It is independent of C.
It is independent of C. Right? So when we have to explain this concept in econometrics, we always say that your dependent variable, expected value of your dependent variable Y with respect to independent variable Xi. So this is not dividing Y by Xi, no. Right? This is not like dividing Y by Xi. It is what is the value of Y in a given model with respect to the value of X. And from this, we come to know that your Y is your dependent variable and Xi is your independent variable. So again, expected value of y with respect to a given x. This is what it means. This is what this thing means. Okay?
Ma'am, once more.
Expected value of y with respect to x, or given the value of x. This is the thing. It's written. Right? So, when we have to find that what is the value of y in econometrics, we always write like your value of y is equal to a coefficient beta 1 plus beta 2 xi. Now, this is known as your population regression function. Why? Because this xi includes all the elements, right? It includes all the elements, and these beta 1 and beta 2, these coefficients are your parameters, parametric coefficients. They are your population parameters because they are determined from the population itself. So we have done the difference between your population and your sample. So population is the one like in which we are including all the possible elements, right? So these beta 1 and beta 2, they are called your population parameters. But whenever you take a sample, for that, we have a stochastic regression function. And in this stochastic regression function, we are going to introduce an error term UI cap. So cap here signifies that we are taking into consideration the sample, right? So we can write our regression equation for our sample to be that the expected value of y with respect to xi is equal to the sample parameter beta 1 cap plus sample parameter beta 2 cap xi plus an error term ui, which will account for all the minor differences between your population and your sample.
And whatever you write is coming after like some
Sorry?
time. There's a lag. I guess.
Sorry?
Like whatever you write is coming after some lag.
What
So
we
it's
write?
not- Yeah.
Oh, okay. Like, is there a lag in the video?
I guess so, ma'am. I don't know. Is it my problem? Manali, you have same issue.
Yes, a bit.
There's a lag in it?
Yes, ma'am.
Sometimes.
In the writing?
Ma'am, like your writing are not visible. After you complete the sentence only, it is coming up.
Oh, okay. So probably with my laptop only, there is this problem with the software, I guess. So let's just see. Otherwise, I'll try to change the connection, right?
Okay.
Okay, so we are,
UI cap is saying that it is just determining the minor difference between the sample and the population, right?
yes. So this UI cap accounts for all the differences between the between the population and your sample. Because population, we know it is free from all the errors because we are taking into account all the elements. But in sample, we always take a possibility of error, right?
So ma'am, if we get something like this with UI cap. So I'm going to consider then and there that it's from a sample, right?
Yes.
I mean,
In
the
any
thing
case,
is from it's not from the population.
not from the population, but from a sample. But then in some models, what happens is that this is so low, it is so close to zero that some models even ignore it as well. That its value does not impact or does not have any impact on your dependent variable. That it is so low. When we say that our sample is so perfect that it accounts for all the characteristics of your population, means the chances of an error are minimal, right? And those errors or those minimal errors we get, they have no impact on our dependent variables. So sometimes in some models they even ignore this as well.
Okay.
You'll come to know, don't worry about that. You'll come to know, you'll automatically come to know when we are using a sample, when we are using a population. But in most of the things, in most of your econometric analysis, it is by default that we are using a stochastic regression function. We are always using a sample because calculating your econometric or doing your econometric analysis based on your census or based on your population is very difficult.
Ma'am, here after the stochastic regression function, which is defined as follow, that y minus xi equal to mu. So what does this y means? I mean the first one.
This is your population value. This y value is coming from your population and this value is coming from your sample.
So here I mean here EY, we are taking into consideration small y.
Small y, yes.
Small y. That means small y means it is from the population.
It is the population. It's not, don't go in for the capital Y or small y. It means one and the same thing. Y is your population and E y by xi is your sample.
So I can write in either way, like capital Y or small.
But it should be that these two, whatever, whether you're writing small or large or in capitals, these two should be the same.
Right. I don't need to confuse myself. Like this is the population and this is the sample.
Okay. So again, why do we add that error term in our model, in our stochastic regression function? It is just to incorporate the randomness in human behavior, right? So principle of parsimony, that is your lesser the explanatory variables, better will be the result. Vagueness of the theory, unavailability of data, poor proxy variables, and interdependence of variables. Proxy variables are like what is the base variable you're using to explain. Like for example, when we are calculating inflation, we use CPI. Right? Or what is the variable you're using to explain a certain economic term or anything. Okay. You're clear till here?
Yes, ma'am.
So ma'am, from the picture, I can say that I'm not the only one who is afraid of econometrics.
No, Manali, I am here.
I was waiting for econometric classes actually, since the very beginning, I feel. Okay, so we are fine till here, right? Let's go on to our OLS method.
Yes.
Okay, so in OLS method, it was given by Carl Gauss. That's the basic thing. So in this case, we try to identify a model in such a way that our population variable minus our sample variable, the difference between them and square, this should be minimum. What does it imply? That the variance between your population and your sample, or your population regression function and your stochastic regression function, this should be minimum. Lesser the variance, better the model, right?
Once for the variance between the
Population regression function and your sample regression function, it should be minimum. The difference between your population and your sample, it should be minimum, right? The square of it.
ma'am, just yi is the population and yi cap is the sample.
So when we are assuming that this is minimum, right? So we can say that our yi cap is equal to beta 1 cap plus beta 2 cap xi, right? This is our stochastic regression function. And when we substitute this stochastic regression function in this, we get summation yi minus beta 1 cap minus beta 2 cap xi the whole square.
Ma'am, here in this stochastic case, why we are not adding up this mu I?
Why? Because we are considering that our error term is negligible. That's why we are saying that it's not always necessary that in stochastic regression function, you always include your error term. So from this, we can calculate our value of beta 1 parameter and beta 2 parameter, right? Sample parameters, these are sample parameters. If it would have been just beta 1 and beta 2, they would have been population parameters. But now we are using beta 1 cap and beta 2 cap. So they are sample parameters. So our beta 1 cap is equal to your y, right? And here we are using the mean of y. Your y mean minus beta 2 cap x mean.
Why we are taking mean here?
Why we are taking mean? Because we say that whenever, you know, like the mean deviation, you remember that deviations from your mean are
Is a minimum.
Right? Minimum. So
Yes.
we are, that is why we are assuming that it is mean. So start using your, you know, statistic concepts here. Okay. And beta 2 cap is equal to your summation xi yi upon summation xi square. Now you need to remember these two formulas as it is, because you can get direct mathematical question based on them. So they will be giving you different values and you have to find your parameters. And I'm actually using the wrong word here. So whenever we are using, whenever we are referring to the coefficients from a population, it is called a parameter. Whenever we are using, coefficients from a sample, it is called a statistic. So these two are sample statistics. Okay. So what are the assumptions, before moving on to the model, what are the assumptions we use in an OLS or simple linear regression model? OLS is nothing but ordinary least squares, right? And the first assumption here is that your model should be linear. So if your model is non-linear in nature, you cannot apply OLS in that. So just quickly tell me, y is equal to a plus bx, linear or non-linear?
Linear.
Linear.
Y is equal to a plus bx square, linear or non-linear?
Non-linear.
Non-linear.
Y is equal to a plus bx plus cz, linear or non-linear?
Linear.
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 Linear, right? So your model should be linear in nature. And then your values are fixed in, your values of x, they are fixed in repeated sampling, in the sense that your values of x will not fluctuate drastically. You know, when you choose different samples from a population, when you're using different samples from a population, the value of x will not change drastically. It will not be affected much. There won't be much variation in different samples from the same population. Okay? And your mean value or expected value of the random error term is 0. So that's why we are not taking any error term here, because we are assuming that your expected value of ui with respect to your xi is equal to 0.
So, ma'am, your UI is representing the random term.
Random or error term.
That means error term, random term, these are all the same thing.
Yes, same kind of a thing. They are used synonymously. So don't get confused while we are doing econometrics between random term and error term. They are used synonymously with each other. Okay. Next assumption is that there is no autocorrelation. Right? So there is no autocorrelation, and by autocorrelation we mean that if you're using different error terms by any chance, if we are using different error terms in the model, so there is absolutely no correlation between them. So autocorrelation is no correlation between error terms. So the covariance between your error terms is 0. Furthermore, we assume homoscedasticity in the sense that even in case of your error term, in case of your error term, there is a constant variance. Your error term is not changing with respect to x. So if we say that what is your variance of error term with respect to xi, right, is equal to your standard deviation square. So this is a constant term, right? It is not changing. If I would have written, instead of this, I would have written sigma I square, then this would have implied that no, the variance is not constant. It is changing with respect to this I.
Once more.
So whenever we just write simple, when we write, now just say, we have a subscript, right? Xi. So you know that this value of x is changing when I is equal to 1, when I is equal to 2, I is equal to 3. It is changing with that,
Yes. Yes.
right? When we write sigma square, this means there is one value, right? One single value. But instead of sigma square, when we write sigma I square, this means that
Different values.
I is equal to 1, I is equal to 2, I is equal to 3, and so on.
Yes.
So this means that the variance is not constant. It is changing with the changing values of I. Right? So whenever the variance is not constant, whenever the variance is changing with respect to I, we say that there is heteroscedasticity. But in OLS method, we assume homoscedasticity, saying that our variance is constant in nature. Then we come to the concept of no multicollinearity, in the sense that when your model, say when your model y has beta 1 plus beta 2 x1 plus beta 3 x2 plus beta 4 x3 and so on, right? When we say that there is absolutely no relation between x1 and x2, or x2 and x3, or x1 and x3. So whenever there is no relationship between your explanatory variables x1, x2, x3, when we say that there is absolutely no relation between your explanatory variables, we say that there is no multicollinearity. But when we say that there is a relationship between your explanatory variables, we will say that there is multicollinearity. So you should remember one thing here. Autocorrelation is bad. Heteroscedasticity is bad. Multicollinearity is bad. So whenever any of these are present in your model, means your model is flawed. Right?
Yes, ma'am. I got it. Yeah.
Kavya is so happy, no? Okay.
X1, X2, X3 are called the explanatory
variables or independent variables. Then, seventh assumption is that your specification of the model should be correct. You should correctly specify which is your dependent variable and which is your independent variable in your model. It should be correctly specified in the model. Next is that there should not be any relationship between your error term and your explanatory variables, not at all. Your error term should be independent of all the variables. So the covariance between your error term and your explanatory variables should be 0. Okay. Ninth is that the number of observations in the sample should be greater than number of parameters. For example, you are trying to estimate, let's just take into consideration your PQLI index, right? So they have 3 variables in the model. So the number of observations to test or to calculate the PQLI index should be at least greater than 3. So at least to identify or analyze or calculate the value of your PQLI, right? Based on 3 independent variables, which is based on 3 independent variables, you should at least ask more than 3 people. You should at least interview more than 3 people. It's not like you just interview 2 people and bring about an analysis for 4 variables or 3 variables. No, your number of observations should be greater than the number of variables involved in your model. So if you are using 2 variables, your number of observations should be greater than 2. If you are using 4 variables, it should be greater than 4. And last is that your variance of the explanatory variables should be a positive number. So if your square by any chance is coming out to be something very different or very vague, then definitely your model is wrong.
in the case of specification of the model should be correct means that from the, I mean, before doing the model, how can we predict that it is an independent model or a dependent? I mean, how can we predict that which variable will be independent and to the other, and which one will be dependent to the other, and how can we predict this?
That's why we have theories, no? So with theories, with reading, with all such things, you know that which is independent and variable. So if I say, if I just randomly put forward two variables, C and Y, you'll automatically know that no, C is your dependent variable and Y is your independent variable.
Variable.
So just go through the assumptions once and see if it is clear. Then we'll go on to the properties of the model. Okay, so we are clear?
Ma'am, in the third assumption, like x bar value or the expected value of the random variable, random term is 0. Like x bar value, so that means we are also considering that
Deviations from the mean.
Okay. That we are considering here, x bar value. Okay.
So moving on to the properties of estimates. Estimates or your statistics or your coefficients which we are doing. First is in case of small sample. When you have a small sample or finite sample properties, right? So what are the properties which should be there? First case is your unbiasedness. Unbiasedness in the sense that your expected value should be equal to your actual value, right? So expected value should be equal to your actual value in the sense that whatever value of your parameter you're getting out of your model using actual data should be the same as what you estimate using a certain proportion of it, or you expect the value to be, right? In the sense, when you take actual data and when you take a representative data or a sample data, it should be the same. There it should be unbiasedness. So this is represented as your beta cap, your actual value of your estimate, that is your beta cap, should be equal to the expected value of your estimate. So in expected value, we take mean values. Mean values in the model should be equal to the actual value of the parameter which you get from actual data.
So, ma'am, for an example, we can say that the population, for the population data, if you're estimating something related to the population, it should be equal to the sample.
So, for example, if I base my model, on the means, of your data, right? So mean value is this, mean value is that, and on the basis of this I form my value. For example, y mean is equal to beta 1 cap plus beta 2 cap, x mean. So this is my expected parameter. But when I use y is equal to say beta 1 cap plus beta 2 cap xi, this is my actual parameter. Based on the number of observations, you are getting your beta 2 cap. This is just using one mean. You're getting my point?
And what about this beta 1 cap?
This should be also like, this is your random coefficient, you know, this is your independent coefficient. Right? It does not have any dependent or independent variable with it. It is like just like that autonomous thing you have.
Okay. But if we write in this manner, like x1 cap, sorry, beta 1 cap x plus beta 2 cap, then we will to see in the same way that beta 1 cap is the expected value and beta 1 cap is the actual value.
Then
I mean, just
no.
Yes.
Don't play with econometric rules, Manali. Don't play with that. You're not supposed to play with that.
Okay.
Actually confuse you because this does not happen. So
Okay.
we are always taking our autonomous term first. That's why whenever we are doing your model, we always take your autonomous model first. We don't do this. No.
No, ma'am. Actually, I thought that it is like you were taking in this manner. I mean, nothing as rule or kind of.
These are just certain unsaid rules we have that, you know, you need to first incorporate the autonomous value in your model and then go on to your dependent or independent variables.
Okay, ma'am. Now I got it.
Right?
Okay.
So this is your first property which should be satisfied. Then is linearity, that the model should be linear. Minimum variance, which we know that it should give you minimum variance. We have done this, y minus yi square, right? This should be minimum in your ordinary least square method. Again, very important. In econometrics, whenever we talk about the term efficiency, so efficiency in econometrics means satisfying both unbiasedness and minimum variance. So when these two conditions, when both of them, they are satisfied by the model, we say that the model is efficient in nature.
Unbiasedness and
minimum variance. Next is you have sufficiency property in the sense that your sample contains all the information regarding your population. So whatever sample statistics you are getting, whatever estimates you are getting after applying OLS, estimates here we have beta 1, beta 2, right? whatever estimates you get after applying your OLS, right? This should contain all the information about your population. And when it does, we say that it is a sufficient estimator. You can use it with, you can use it in a similar way as you use your population parameters.
But ma'am, beta 1, beta 2, you said like the cap 1, it is the statistic.
It is the statistics. These are the estimator statistics. They're all the same terms.
Okay, okay. All the estimates should contain all the data of the population, right?
Yes, yes. Next is your minimum mean square estimator in the sense that you have a minimum mean square error. Minimum mean square error. So in this case, your mean square estimator is equal to the expected value of your beta cap, right, minus your mean error b. Small b is your mean error square. And when it is minimum, it means you have an efficient estimator. You have a good estimate, or you have a good sample, or your model or your values are correct.
Means good estimators or sample, right?
Sample statistics.
So basically we can say that beta 1 cap and beta 2 cap are the tools of evaluating different data from a population, or from a sample, not a population but a sample.
These are telling you, these are the basic estimators which actually tell you how efficient is your model or how good is your model. So these beta 1 and beta 2 are actually used for testing of hypothesis. So we always talk about blue properties in your OLS. This is best, linear, unbiased, efficient estimators. So we say that whatever estimators we get from applying OLS are the blue estimators. So they are best in the sense they have minimum variance, they are linear in nature, there is unbiasedness, and they are efficient in nature. So estimators from OLS method, we get whatever estimators we get from OLS, all of them fulfill the blue properties, or they're the blue estimators who fulfill all these properties, blue properties. So this was the case of small samples. What about large samples? Right? So whenever whenever you are trying to increase your sample size, the chances of errors, do they increase or do they decrease? Sorry?
Increase.
Increase.
Yes, I will say.
If I say that more the variables, more the observations, isn't it that it is better for the model that you're moving closer to your population?
Yes, yes.
So
As you said, for PQLI, that one.
chances of errors, they decrease. Okay. So in large samples, these properties should be satisfied. Again, first property is of unbiasedness, right? So your sample statistic should be equal to your population, or it should be equal to your expected or mean statistic. Right? So your parameter should be equal to the mean of this parameter. The actual value should be equal to the mean value or the expected value.
Problem once more.
In the case, it's the same as your unbiasedness property of small samples, that your actual value should be equal to the expected value.
Value.
And now we have another term, that is your consistency, right? In case of consistency, right, whenever if you have an asymptotic unbiasedness and asymptotic variance, right, that it is not changing, asymptotic, it is not changing the properties of your model. So your unbiasedness does not change, your variance is constant. This means that your model is consistent in nature.
Variance is also constant, right?
Yes. And in case of large samples, you have an asymptotic efficiency. That is efficiency for large samples or when you're adding more variables, right? So asymptotic is when you're adding additional variables, your model is not changing with that. So your estimates you get from large samples, they're called asymptotic efficient when your beta cap is consistent in nature. That again, it is not changing with additional values. And again, you have the minimum variance. So minimum variance, beta cap is not changing, and your unbiasedness property, when it holds, you say that your model is asymptotic efficient.
Ma'am, here it is minimum variance as well as unbiasedness to be maintained.
In case of minimum variance, this one, that is your asymptotic consistency. The only addition in asymptotic efficiency is that your parameter or your statistic or your estimator is consistent. It is not changing with additional values.
One thing that beta cap, we know that beta cap is actually from the sample. So like expectation of beta cap means we are taking the mean out of it.
Mean of all that values, all those values.
I mean beta 1 cap, beta 2 cap, like this.
Mean of X from X. Okay. So Gauss-Markov theory says that whenever we say that your properties like your linear unbiasedness and your efficiency, when they're satisfied, then we say that whatever estimators we get from them, they are called blue estimators, and they satisfy the blue properties. But then we have is the multiple linear regression model, in which, like we said, that there are more than one explanatory variables. So we have beta 2 x1 plus beta 3 x2 plus ui. So this is a multiple linear regression model. These are the slope coefficients. This is the intercept term, right? And even in case of your multiple regression models, the assumptions are the same as your OLS model. But whenever we say that if any of the violations or any of the assumptions of OLS are violated, we come with we can come with any of the three problems or all of them together. That is your multicollinearity, heteroscedasticity, and autocorrelation. And all of them are problems for your model. And if they arise in your model, means now you have to take corrective measures to solve these problems. Do you have the strength to do multicollinearity? We can take a 2-minute break if you want.
Kavya left now.
Huh?
Kavya left.
Internet might have. Okay. So do you want to continue, Manali, or do you want to stop here?
It's up to you, ma'am. Like you can do it, or we can do all together with Neha and Kavya.